Okay, let's get the show on the road. I want to show you today how to start task 2 of assignment 1. And the assignment looked something like this. It was the Excel spreadsheet you got with Cape Titan coordinates and Hartbees Hoek coordinates, and you've also got the ECEF coordinates, so you don't have to worry too much about those. One thing about the three-dimensional transformation we need to remember is that the translation parameters, rotation and scale parameters are bound to be very, very small. So the translation parameters are large, but these things are small. So the initial rotation parameters that Deacon recommends are therefore not necessary. His B matrix, because we didn't calculate rotations and initial translations, which he did, we need to augment his B matrix to allow for corrections to your translation parameters. Now let's have a look at what Deacon's B matrices look like. Now, first thing you need to do is you need to understand the problem correctly. What we want to do, we want to go from an XYZ system, which Deacon has got here in his picture, to a east-north-up system, which is the system he uses to do his surveying. In other words, that's your original coordinates. You need to transform them so they look the same as these coordinates. And you do that by rotating the axes, like he shows over here, multiplying by a scale factor, because there'll be a scale factor from here to there, and then adding the translations between the origins. Now, let's have a look and see what the B matrix or D matrix will look like to calculate those. So if you look at his transformation around here, again, that's the east-north-up. After translations to the origins, remember, that's why the bar is on the top there. And then he multiplies by the scale factor, initial scale factor, which we use as 1, plus the calculated scale difference, multiplied by a calculated difference in the rotation matrix, which we didn't do because we only calculate a small rotation matrix at the end, multiplied by this plus your errors, of course. Now the B matrix sits over there, it's this one. And you can see your solution matrix, Deacon solution matrix, you've got a delta omega, a delta phi, and delta kappa, and a delta lambda. That's the changes in your rotation about the x-axis, the y-axis, z-axis, and changes in the scale factor. We didn't calculate the scale factor, we used 1, we didn't calculate any orientation, so what we get out of there will be our, although we call them deltas, will be our initial orientations that we calculate, and that will be the only ones that you need. Your B matrix that sits over here, if you look at the zeros that are filled in there, where do they come from? This is for the x coordinate, that top row. Now there's no rotations in the x coordinates, so there's 0 delta omega, just delta phi, delta kappa, and a delta lambda. Obviously delta lambda is applicable to all the coordinates. Same here, your y coordinate does not rotate, or the phi, there's no phi rotation over there because it's only the x and z axes that turn. Similarly over there. Now this B matrix that he's got here, for every coordinate, because this is for one coordinate, for every coordinate you have a B matrix like this, and they partition. Now what he did in the end is he calculated these B matrix, and instead of making it a 0 and a 0 and a 0 like that, he just organized all the x coordinates, all the y coordinates, all the z coordinates for all three coordinates that he's got there. And we're going to do exactly the same with our transformation. So, what I've got here is not your problem, it's another problem which was done in Ingwalala in Malawi. At least not Ingwalala, Karonga in Malawi. So it will look a little bit different. There's only 4 control points, not 6 like you have. And the data that I got was over here. Initially, I got lots of coordinates in UTM zone 36 south, arc 1950, and some coordinates in UTM zone 36 south, WGS84. Now those are the 4 control coordinates that I got. We initially calculated lots of stuff over here for just by doing a XY shift in the projection itself. So you'll see that our answers aren't all that correct right towards the end. But once you've got your X, Y, Z coordinates, or your X and Y coordinates, without the scale or without the constants like they have in the UTM, you can calculate Earth-centered, Earth-fixed coordinates for these, and then we can proceed with the 3D transformation. So what have we got? We've got our arc 1950 X, Y, Z, Earth-centered, Earth-fixed coordinates, all of them, and we need to calculate the centroids. So the first thing we need to do is we need to calculate the centroids over there, and these centroids are simply the averages of those. So if you look at the centroids over there, you'll see that the average, if you go in there and just have a look there, for instance, I don't think you can see this properly, it's the average of that. And similarly for that one, and for that one, and for that one. So for all of them, and similarly over here, we've got our averages over there, which is the centroids. And you can see that your dx, dy, dz, which is simply the difference between these and these. Now if you look at that one, it's that one minus that one. Always the one where you want to go to minus the one where you're coming from. And the same with those. Now what I did is I just put my coordinates down here, the same as those, arc 1950, I put them down here for ease of use. You don't have to do that. And the same with my WGS84 coordinates, I put them down there also for ease of use, because it's just easier for me to work horizontally, because over there I've got my X, Y, Z horizontally. And you'll see there's some other differences as well when we put these things horizontally. So we go from the original coordinates to the centroids by doing what? Simply subtracting that one minus that one. And the same over there, subtracting that one minus that one. And we go to all, we can get all the centroids, which is then more or less on the same system. You can see that one and that one is nearly the same, but there's a small difference which we calculate in our F. It's N15 minus L15, so it's that one minus that one. And same for all the others. So that's your F matrix. That's your the differences between the coordinates. Now your B matrix, if you go back to Deacon, your B matrix is, if you go to right over there, Yeah. Your B matrix consists of, remember he wants to go from the X, Y, Z to the eastings and northings. So the B matrix consists of the X, Y, and Z's, in other words, the original coordinates. So my B matrix needs to consist of that, and let's go with the first four terms, the same as what Deacon did there. The first column is 0, I've got 4 coordinates, so I've got 4 zeros over there, and then over there I've got my I've got minus 1 times L17, so that's minus 1 times, and I think L17 was this one, minus 1 times the ARC 1950 datum over there, so that's minus the Z of that coordinate. Similarly, that one is the same as the Y coordinate, and this one, yeah, and this one will be the same as that one. And so you make up that initial square. Then, of course, we said we need a dx, dy, dz, because this will account for your d omega, d phi, d kappa, and d lambda. Then we still need columns for the x, y, and z, dx, dy, and dz. Now, obviously, they are going to become 1 in here because that's for your dx's. And as you carry on with the B matrix, you'll see that the pattern repeats itself, and there's a 0 and a 1 in those 4, and then there's a 0 and a 0 and a 1 in those 4 to account for the dx, dy, dz. And that's how you start it. I hope that gives you some idea of how to carry on with this assignment. And if you've got any problems, as usual, just drop me an email and I will attempt to answer you fully. Bye bye.